So we have to. Okay, Dale is also here, and I don't. I don't see our external yet. Oh, there. Okay. All right. Let's get started. Um, yeah, thank you, Rich, for the introduction. It's been 5.5 years. Yeah. So this was me in this room in 2019, my first year student. Fresh faced, young, uh, and now no longer as young, but still as excited. And I have some more beard now, but and a lot of white hair. But yeah, it's been a very memorable time, and I look forward to telling you what I've been up to since then, right? And so it's sort of like nice coming around because this is this exact location, CS333. You don't see it there, but that bunch of curly hair is Fernando's hair. uh, and yeah, all right, let's get started. What have I been up to? Well, my goal for my dissertation has been at a high level to develop simple and practical learning algorithms from first principles for long-lived agents. Okay, and so yeah, these are fairly generic terms, but it will soon be clear what they mean for sure. And in order to do this, I worked on several topics in my PhD. I will not tell you all about all of them, but in particular, I'll tell you about one-step average reward methods, their extension to multi-step average reward methods, and then an idea to improve discounted reward methods. And yeah, surrounding these topics, like for example, in the beginning, I worked on looking at the pros and cons of the discounted formulation versus the average reward formulation and whatnot for the continuing problems. So that was something. I also worked a bit on developing a suite of continuing problems so that I can do this research, right, among other people, and now hopefully other people can too. Then extending all of this to the options framework. Then outside of this stuff, some planning related things such as planning with expectation models for control. And yeah, generalizing in the action space with policy gradient methods. This was some internship work. But yeah, if you're interested, these are some references for all of them. But like I said, I'm going to focus on these three things. Okay. All right. So that's what the outline is going to be. I'll quickly tell you what problem I'm trying to solve, and then how do these three things come in. And then I'll end with, uh, what have we learned? What are the things left to do? And there are many of them, and acknowledge some people out of the many many that I would like to thank. All right, so the problem setting is we are dealing with continuing problems, right? So the usual RL diagram. There's agent interacting with the world. You observe something, take some action, observe some reward, and this agent environment interaction just keeps going on forever, right? There is no episode terminations, resets, cutoffs, timeouts, nothing. And what are some examples? Well, maybe a lot of us have worked with Compute Canada, right? So there's a limited compute cluster, and there is everyone is trying to submit their jobs. We all have different priorities. Maybe profs have some higher priority, and there are allocations, and then there is some controller trying to decide how to allocate this limited resource to people, right? And so they have to make the decisions throughout till the time that they're on, basically, right? So that could be 24/7 for many, many days, weeks, months, years. Similarly, imagine self-driving cars that are roaming around. Uh, and so after they drop someone off, what is the best place in the city to go to so that you get another ride quickly, right? So as to maximize revenue. Uh, so this might seem like something in the future, but it's already happening in cities like San Francisco, which is crazy. It blows my mind. And then looking further, things like Mars rovers and stuff, right? That you have this rover going around zapping interesting rocks, and it's doing this throughout its lifetime, and maybe one day it bumps one of its sensors, it gets bent, and from the next day on it's seeing the sensory data like this, right? And it has to learn and adapt and continue doing that throughout its lifetime. Cool. So those are what kind of problems there might be, but to make progress, it helps to formulate it mathematically, right? To say something more precisely. So if this represents the stream of experience of the agent, right? So starting with, let's say, some state 0, action 0, reward, state, action, reward, so on and so forth. Um, the goal in RL is to maximize reward, right? And you can simply write this as the sum of rewards index t to infinity and find some way of behaving, which I'll call a policy pi, such that this sum of rewards is maximized, right? And remember, I told you that these are like continuing problems. There is no end to it. So that means you are literally summing up infinite terms, right? And that sum is infinity unless all of those terms are 0, right? And so in order to make sense of this, what helps is maybe if you look at the average, right? So, okay, this is a complicated looking term, but here is what it is. This is the sum of all the rewards till n divided by n to get the average. The expectation term is to, average out the noise, and the limit n tends to infinity is to say, okay, you want to do this over a long time, right? To maximize reward over a long time. So find a way to behave, maximize pi such that our pi is maximized. That's the average reward formulation. Alternatively, there is another way to make sure that a sum of infinite terms is finite, and that is through discounting, right? That you could have a discount factor between 0 to 1 such that the sum of infinite term is still bounded, right? It will be some finite quantity. And then you can define, what is the expected sum of discounted rewards from every state if you follow this policy pi, and then try to maximize that, right? Find a policy pi such that this value is maximized across all states. Okay, this is the discounted reward formulation. So in this talk and most of my PhD, I have focused on the average reward formulation. And yeah, like I said, I looked into the pros and cons of it. And yeah, this is what I decided to work on. And if you want to know more, you can look at this paper. But okay, so the average reward formulation. This is the average reward. Now, just like in the discounted case, you can define an expected sum of rewards, right? Which is the value function. So for some state S, starting from that state S, this denotes how much more reward are you getting than the average, right? That is what this value function is encoding. And yeah, just to see some similarities, so there is just no gamma now, and now you're subtracting an average reward at every step. Okay, so this is called the differential value function, and that's a nice name because it involves a bunch of differences, so it all makes sense. Okay, so one of the problems within this average reward formulation is to estimate the average reward and the differential value function corresponding to some policy pi. That's called the prediction problem. Alternatively, you could also want to find the policy that maximizes the average reward, right? So that you can behave in a way that you get as much reward as possible. This is called the control problem. And so the harder version of these problems is when you're trying to do this when you're behaving according to a different policy B, right? That the stream of experience that you see is according to some other behavior policy B, but you're still trying to estimate the average reward and the value function of some policy pi, right? So that's called the off policy problem. Okay, so that was the background that we need. Now we can start understanding each of these things, right? Okay. One-step average reward methods. So the first thing that I worked on was one-step average reward learning methods. And for the sake of this talk, I'm going to focus on the off-policy control setting, which is arguably the harder of both problems, right? And so there is a rich literature in the average reward formulation, and it's almost as old as Markov decision processes, right? So from the 60s, people have been studying this in the dynamic programming literature. In RL, it's relatively recent. I mean, so Schwartz pioneered this back in 1993, which is more than 30 years ago. So, recent is a relative term. But then, yeah, there was a flurry of work. People have been doing, lots of nice incremental update improvements. Um, and so what is so yeah, this has been happening all the way till quite recently. But one of the things with these sets of methods is that either they don't have any convergence results, or if there are any convergence results, they require some special knowledge about the problem, right? Maybe like the mixing time of the MDP, or like the diameter of the MDP, whatever those things are. But then in 2001, Abunadi, Bortsekas, and Borker took a big step forward. And Yeah, and so our work builds on that. And so I'll have to tell you something more about that. But before we do that, let us take a step back and put ourselves in the perspective of the agent, right? What is the problem that the agent is trying to solve? So one of the things it has to do is to estimate the average reward from data, right? So it has some stream of experience. It is experiencing some rewards. Okay, so if I want to estimate the average reward, this is the policy that generated them, some pi. I could just do this, right? That if at time t I have seen t rewards, I just sum them up, divided by t, that's the average reward. That's my estimate of the average reward. It's a good estimate. Now, if I see the next reward, which is rt plus 1, I can update my estimate by, you know, the old thing plus 1 over t plus 1, new reward minus your old estimate. And I can generalize this term with just a scalar step size term, right? And this is all very familiar. And this is just a weight, like a exponentially recency weighted average of the rewards that you see. Okay, all good. And we know that if we keep doing this till infinity under some conditions, this will converge to the average reward of the target policy, which you are interested in, right? And a quick intuition of why this happens is because if you look at what this term is, that limit of sum of expectations that we saw earlier is this expectation term, right? And so it's sum over all states, the steady state distribution over the states that you see, all the actions that you can take, the rewards that you see in those things, and the reward. And so this update rule basically comes from this general rule of thumb, not rule of thumb, like it's a, yeah. The new estimate is the old estimate plus step size times this new target, where target is this thing in the expectation minus the old estimate, right? This is what this is. New estimate is old estimate plus step size, new target minus old estimate. Cool, we do this, this works. But what if we were in the off policy case, right? Now, so far we're looking at the case where the rewards were generated by the policy that you're interested in. But now let's say they're generated by some other arbitrary policy B. If you kept doing this, what would happen? It's not a rhetorical question. You can answer. Yeah. Yeah. So we, as Adrian said, R infinity will converge to RB, which is the policy with which you are generating the data. And that's because, now this is this expectation, right? You are taking actions according to B. The distribution is according to B, and that's what will happen. But, there are many students from the 609 class. We know we can use importance sampling ratios, right? Does that solve the problem? Okay, so if you just use importance sampling ratios, what will happen? So there is R. Now you're multiplying a pi by B. So that B will get cancelled. So you have a pi. That's good. That's what we wanted. But there is still a mismatch here, right? This is still according to pi. We have not done anything for it. And so this R infinity, we know that, okay, we are doing something different. So it won't go to RB, but it doesn't go to R pi either. Okay. So the importance sampling ratio is not enough. And now I'm going to claim that, okay, if you do this instead, which is update your average reward, not with this conventional error, but with the TD error, right? Then R infinity will go to R pi, even if you're behaving according to this arbitrary policy. Okay, cool. Okay, now we'll see why this is the case. But what else do you know gets updated with the TD error? The value function, right? And so why does that work in the first place? So if you want to estimate the values from data, this is your data. This is, the discounted value function in case of the action values. Okay. It follows this recursive Bellman optimality equation, right? That for the optimal policy, this recursive term is true. This is the Bellman optimality equation. Okay. And this is the update for Q learning. one step Q learning. New estimate is old estimate plus step size. Now this term, remember this old rule that we have. This update for Q learning did not just fall out from the sky, right? Somebody looked at this and they were like, okay, this thing inside the expectations, I can use that as a target in my sample-based updates, and then just use this general rule, right? And that's good. This is the TD error for this discounted case, and this is the discounted Q learning algorithm, right? And it has nice convergence properties. Okay, so we can do something similar for the average reward case, right? So on the right, now we are looking at the differential value function, which is for the action values. It also follows a similar recursive Bellman optimality equation. And so if you again follow this general rule, you'll say, okay, I can update it as usual, take this term inside the brackets, this expected value. Instead of that, I'll just take a sample of it and then again use this general rule. Okay. And that is the TD error. Okay. And the only thing difference, like algorithmically, the thing different between these two is that now you're subtracting the average reward and now there's no discount factor. That's it. Right? Algorithmically, they are very similar. And the extra thing that I just said was that if you also update the average reward using the TD error, just like this TD error, uh, this algorithm also converges to the uh, optimal policy, and these Q estimates will also converge to the differential value function of the optimal policy. Okay, so now I'm motivated where you've seen this TD error updates before, and now we'll go back to how this makes sense for the average reward, right? Okay, so back to estimating the average reward from data. This is the Bellman optimality equation again. Remember, the update for the values came by taking this quantity and just sampling this and using it as the target, right? Okay, now I'm going to rearrange some terms of this equation. This R bar, which is the average reward, this does not depend on this next state reward. It's just under certain conditions, it's a scalar that does not depend on just initial starting state or anything like that. So I can take it out of the brackets. Okay. Now I can also take it on this other side, right? Doesn't make a difference. And I also bring this thing on this side. Now again, look at this term. It does not depend on next state and reward. So I can take it inside the brackets. Okay. Now look what we've got. We've got a form for the average reward. It does not depend on the like this initial state S, only on the next state and rewards. And now we can use the general rule, right? We can take this quantity inside the brackets, inside the expectation basically, and use it as our target. The new estimate is old estimate plus step size times new target minus the old estimate. That's your TD error. These are the same quantities. And that's why you can do this. And this is a convergent algorithm, right? So my co-author Yi, who is really good at all of these kinds of things, he showed the convergence of this algorithm and a few others that we proposed in this paper, like the planning variants of them, the prediction variants of them under certain technical conditions. And yeah, note that I've changed something from the last slide, which is I replaced this beta t step size with something called eta alpha t, which is just an aesthetic change. It does not change anything functionally, right? Any value that you present by a beta t scalar can be represented by eta alpha t. Okay, it's just neat to use, and I'll show you later. Okay, so remember I was saying that there was a big step forward in 2001 by these three authors, and this is basically the algorithm that they had proposed. They called it RVIQ learning. And if you look at the differences between the two, it's basically just this. They don't have an average reward estimate, just they are subtracting something which is a function of the current estimates of the action values. Okay, and the examples of F could be just the value of a single state action pair, right? So you choose, let's say, your starting state, starting action, take that as your S0, A0, and always subtract its current estimate. And they show that this algorithm converges. Okay, then and this F is a very general thing. It can also be like the average of all the action value pairs, right? And so that was the good thing about this algorithm, that it, for a very big family of algorithms, depending on how you choose f, all of those algorithms are convergent, and then you can use them. Now, as a practitioner, one might ask, okay, you have 100 choices. Which one should I use? Right? And there's always that dilemma. And okay, so you want someone to tell you, okay, maybe use this one. This will be good. It will work in most cases, right? So, so unfortunately, we don't know that, at least just by looking at it. But then we did some analysis, and it turns out like it works well when the state action pairs that occur in the agent's data stream are the ones which occur frequently under the optimal policy. Okay. Now you don't really know that before, right? If you did, like, you sort of know some parts of the solution to the problem. If you already knew the optimal policy and what are state action pairs occurrent under it. But okay, what can you do? Like in the tabular case, you can just run everything, right? You can run every single state action pair separately and see how it works. So let's quickly do an empirical comparison. I'm going to, so this is like a typical learning curve, right? On the x-axis, you have time steps, which is the number of interactions between the agent and the environment. On the y-axis, you have something called like the reward rate, or which is just a sliding window of average of rewards over some time, right? And average over 30 runs. And so performance begins somewhere, relatively random performance, rises up, stabilizes a bit. Okay, and so this is for like some parameter values, right? I set some values of alpha t, eta t, or f, and then you get this curve. But now you can also summarize this curve by taking like the area under the curve, right? Which will tell you how fast learning happened. If the curve was like this, the area under the curve would be quite small, right? If it was like this, it would be quite large. So it sort of gives you an indication of how the rate of learning, right? Okay, so that's what we are going to look at in these curves, which is on the x-axis. X-axis, it's no longer time, but a step size. So this is a sensitivity curve where each point will be this area under the curve, okay, for an algorithm, and which is, so that's the y-axis. So it looks like something like this for differential q-learning, which is the algorithm that we have been discussing, that this eta parameter that I told you about, if you keep it fixed to, let's say, 0.125, and your step size is small, then performance, this area under the curve is this value. But if you had set it to this, it would be much higher. Okay, so that's the general trends, sensitive parameter studies. And so they look, they don't vary too much with the value of eta, right? Which is good. Now let's do it for this RVIQ learning, where we had different choices of what the f function you could choose, right? And it looks something like this. Now there are many, many lines here, and each of them is like if you take, there are 88 state action pairs in this tabular problem. Oh, maybe this access control problem is basically a version of like the Compute Canada scaled down version of it, basically, right? And so there are just 88 state action pairs, and I took each one of them, set them as the reference function, ran the algorithm, and that's each one of these lines. And I have marked some like 87, 43, state number 21. And I also marked like the max and mean, if you take like, mean over all state action pairs, the max of them. And so as you can see clearly, performance depends a lot depending on what reference function you choose, right? Sometimes you could get lucky. Let's say if you had chosen state action pair 55, but sometimes you could behave very poorly, right? But the thing is, you don't know this upfront, right? And you also cannot, right? You can't know upfront which state action pair is frequently occurring under this thing. And so yeah, while this algorithm is super general, like it is a whole family of algorithms, which is very nice. The one thing that differential q learning gives you over it is that you have this explicit average reward parameter. We tell you how to update it. You have one parameter for it, and it's relatively easy to set, right? Like performance doesn't vary too much. There's a lot more I could show you, but I have to move on. So I'm going to wrap this up by saying, okay, differential q learning is a convergent algorithm for off-policy average reward control. It does not require a reference function, can be relatively easy to use. And then the prediction version of it is differential TD learning. That's also a convergent algorithm for off-policy average reward prediction. It estimates both of these things accurately. There are nice convergence proofs for it. Also relatively easy to use. And more experiments, the planning versions of these algorithms, all the convergence proof, you can look at this paper. And okay, so let's connect it back to what my goal was, right? That simple and practical algorithms from first principles for long-lived agents. So it's simple, like, you estimating the average reward is super easy. Just use the TD errors you already have. It's practical in the sense that it's relatively easy to use based on the parameters, and everything is based on first principles. I walked you through some of them. But there's a lot more that needed to be done after this paper in 2021. So the first thing and the most obvious thing is that the results in this paper were all limited to the tabular case, right? So which is nice for pedagogy, and results should exist for it. Uh, but then we have grander ambitions, right? So we want to similar results for function approximation, and these methods are also like they had one step consequence of actions, right? And then we all act very locally, but we think at a plan at a very high level, right? So we also want our algorithms to do it, and we actually worked on this. So he and I have a paper on average reward extended to options, but I will not discuss that here. And finally, all of these methods are that I discussed so far are one-step methods, and I haven't told you what exactly that is, so I'm going to do that now because that's what I'm going to improve on, right, in this next part. Okay, so multi-step updates as opposed to one-step updates are something like this. So let's say you're the agent. This is a grid world that you are initialized in and you're trying to learn. Now, I am telling you that there is a +1 reward if you bumble into this state somehow, but the agent doesn't know that, right? So let's say it starts somewhere here, goes around randomly, and somehow stumbles upon the reward. It gets that +1, and now if it used a one-step update, it would update its value function and hence its policy like this. Just the one before which led to the reward gets a non-zero update. All the other updates are 0 because we initialized everything to 0 and whatnot, right? But if you use a multi-step update, in a single update, this is how your value function or your policy would change, right? There is sort of this fading memory of where you came from, and then you make updates for all of that. And yeah, clearly you have done more credit assignment than what you had done here, and this can be efficient in many cases, right? And so remember, I'm talking about model free cases. There is no model. You can't sit and think about all the updates you could have made. So this is just a single model free update. Okay, so this is desirable. We want to do this. So let's start with the simplest case, which is on policy prediction. But I'm going to change one thing, which is that I'm going to go from tabular to linear function approximation, right? So now we are going to, instead of observing the state of the problem, we are going to observe some features, and then we are going to linearly combine them, and that is our estimate of the value function. Okay. Now, in this previous one-step work that I was telling you about, this was the differential TD algorithm, right? You update your weights using the TD error, you update the average reward using the TD error, right? Everything was nice. Now, what's the multi-step version of this? So it looks very similar, and I've marked the changes in blue, right? So instead of this feature vector here, now you have this ZT, which is this what we call an eligibility trace vector. And that is basically the fading memory of the past that I was talking about, right? And it can be updated very computationally cheaply with just this sort of linear update. Okay, nice. Now let's call this algorithm 1. And remember, this is the on policy case, right? We did all of this business in this first part of the talk where we motivated how you can update the average reward using the TD error for the off policy case. But in the on policy case, you could just do this, right? Which is your sample average of the uh, rewards that you see. And of course, yeah, this is indeed an algorithm, average cost TD lambda. And back in 1999, Sitsiklisyan and Roy showed that it converges even with linear function approximation. And there are these strong bounds as to where you converge to, how close is it to the true solution, blah, blah, blah. So I did something similar for algorithm 1, which is, again, showed that it converges under very similar conditions as that one. So I gave a full 1-hour talk about this recently, so I'm not going over that again, but I'll just tell you like the high level 2 steps that I learned in my first excursion into theory, right? That, okay, what I've learned about proving convergence of these sample-based algorithms using the what's called the ordinary differential equations approach is that there are just two broad steps. Okay, lots of words show that the sequence of iterates, which means like basically the sequence of parameters that you have, right? So W0, W1, all the way to WT. We show that it is bounded and asymptotically converges to the solutions of a ordinary differential equation. And then you show that that differential equation has a globally stable equilibrium point, which means once something reaches there, it won't move, right? Which is what you want. And so yeah, so following this approach, proving the convergence of algorithm was fairly straightforward based on what Tsitsiglis and Van had already done. The result is straightforward, but the journey was definitely not for me because I'm not a theorist, right? And but at the end result is fairly straightforward. But that wasn't the goal, right? The goal was doing all of this was to be able to do something in the off policy case, because no such algorithm or convergence result existed in the average reward case for multi-step algorithms, and that is what I wanted to do. And so I was like, okay, this is good. I've gotten some experience. Now it is just one step ahead, right? And now I come back. If you go back to like what the one step off policy updates were for differential TD, the things in the orange are the only change, right? Importance sampling ratio. You just add it on both of the updates, everything works. Strong convergence guarantees. Great. Uh, by the way, I'm talking about the tabular case again, right? The simpler case. And so, okay, so if you say what should be the multi-step version of it, okay, this is what we had. Algorithm one, this was the on policy one. You had a trace, you updated the trace. But now to make it off policy, one simple thing is now you again add an importance sampling ratio here and to here so that they are both here. And I'll give you a second to stare at it and say that if you substitute lambda equal to 0, you get the one-step algorithm again. Okay, timeout. Trust me, it is the case, right? So it is a generalization of the one-step method. And I'm going to call it, because it's the off policy version of algorithm one, I'm going to call it one off, right? And the choice of the name is very apt, as you will soon see. Um, so to so in this, I told you about step one, step two, and one of the things you have to do as part of this step two is analyze like a matrix corresponding to the algorithmic updates, and this is called this matrix is key to convergence, and so that's why people also call it the key matrix. And in my case, it's the A matrix, right? Okay, so for algorithm one, it looked something like this. Details are not important, but I could show that this is Hurwitz, or it has, all eigenvalues have real parts which are less than 0, and which basically says that, that there is an asymptotically uh, equilibrium point is asymptotically globally, it's a global equilibrium, blah, blah, blah. Doesn't matter. So we could show this for that algorithm one. For algorithm one off, I realized that this is the matrix for it, right? So all I had to do was again show the same thing, and I tried for many days, weeks, months, and yeah, then the doubt started creeping in that maybe it is not really the case. So I went to Janie, and Janie is a postdoc with Rich, who is an expert in RL theory, right? And especially like convergence of RL algorithms. I showed this to her, and she was like, "Oh, maybe this is not Hurwitz." I was like, "What? Like, man, that is." I've been doing this for months. Like I showed, all the step one and all of those other things. This was just the tiny final thing remaining, and then she suggested, "Okay, why don't you just see if there's a counterexample, right? Because that's one way to show that something is not true." And turns out there was a very easy way to check it, right? Instead of trying to do all of this linear algebra that I was trying to doing, you can just randomly generate matrices, which are stochastic matrices like p pi, some distribution db, and you can just try like a million of these combinations and see if any one of them fails. And it failed like almost immediately, right, for like most of the things that I tried. And yeah, as you can imagine, that was not a very good day, because then I just proved to myself that this algorithm cannot work, right? uh, but anyway, back to the drawing board a few weeks later. I was like, okay, this is what we started off, one step off policy. We tried this algorithm one version of it, tried to make it off policy, but it did not work. Why did it not work? Like, this is remember, I told you I'm taking a step back here now, back to the tabular case, just multi-step average reward tabular off policy. This is the easiest case in the off policy case. If you can't do this, what can you do, right? So now if you look, so there was this another attempt that I made for this algorithm, which is, it looks more symmetric, right? If you don't look at just the details, just blur your eyes. There are two rows here in orange, two rows here in orange. Here they were, a little wonky. One is in the updates, one is in the trace. But anyway, let's call this algorithm 2. And if you look at the this key matrix for it, it looked something like this. And then I could show that this is Herbert. And not just for this algorithm that I just showed you, this corresponds to the special case when this G vector is a 1 vector. If the G vector is a 1 vector, you're basically looking at this algorithm. But if you choose some other value of this vector, as long as it's non-negative and at least one element positive, you basically get another family of algorithms. And this proof basically applies to all of them, right? So we were having trouble finding one algorithm that it worked, and we stumbled upon a whole family, which is great. And I was very happy with it because this is my first theoretical venture, right? And it took me 2.5 years or something to get this done, but it finally was, and I'm very proud of the results. Even if if you look at it, is like it's not something like it should exist. It's not something mind blowing, right? Some results like this should exist, but I was the one to show them, right? And so that was the cool part because I never had any RL theory training. Anyway, takeaways. I'm not showing you any experiments because I have proved that these things converge. So basically, if all the experiments show that I can write bug-free code because it will exactly converge to the solutions that I showed. But if you're interested, you can talk to me about it. So algorithm 1 is a convergent multi-step algorithm for on-policy prediction, but with linear function approximation, right? Algorithm 2 is a member of a whole family of off-policy methods for the tabular case, right? And this is the first convergence result for the multi-step off-policy setting. And both of these are extension to the differential TD learning work from before. And this is, again, let's connect it back to the goals, simple and practical from first principles. So lots of theory, so clearly first principles. But yeah, still simple, right? Like you just have to update uh, the usual parameters now with just a trace parameter. Um, Practical, that part I didn't really show you, but this is also quite robust to the parameters that you can set. And as if there are any roboticists in the room, or you might have heard Khurram saying, for example, that for any real world sort of applications, you have to do something like TD lambda, right? You can't use one step methods because there is always a gap between when some action was taken and a few hundred milliseconds pass and then you see some effect of it, right? And if you're just doing one step, there is no learning signal there, right? It just cannot work. So you need something like multi-step algorithms, and now we can do this even for the average reward case. And of course, you can look at the whole convergence analysis experiment, blah, 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 in this paper, which we are submitting to a journal soon. And there are, of course, we are not done. There are many things to do. The results can be further generalized. For the off-policy case, we've just gone to the tabular case, right? And you know that there is this whole area of gradient TD algorithms, emphatic TD algorithms, and I haven't even touched any of them. In the case of linear function approximation, that is a whole dissertation in itself, and I encouraged people to think about it. I think Jiamin has already made some progress with the emphatic stuff. Yi did something with the gradient TD stuff, but there's a lot to do. And just like I've been talking about this family, and I also talked about a family in step 1, and there I was sort of criticizing it, right? I was saying, oh, here is this whole family, which is great, but which one should I use, right? Like, I'm a practitioner, I want to use something. So which one of this whole thing should I choose? So we haven't done this analysis for this algorithm, right? I've just told you what this algorithm do, which is a very sort of, it has a nice interpretation, right? You are just updating the average reward with another trace parameter. So everything is nice and explicit, but it might not be the best among this whole family, right? And work needs to be done to figure out which one of them it is. Okay, finally, we can we can switch tracks a bit and come to an idea to improve discounted reward methods, right? So far we've been talking about average reward methods. Now let's go to something which is, maybe more of you are familiar with this part of the thing, right? So I call this idea reward centering, and it is a super simple idea, which is from the stream of experience that you see as the agent, just do this: estimate the average reward of the stream of the rewards that you're seeing and subtract it. Okay, what does that mean? So if this is the Q learning update, the discounted Q learning thing, the only change that you make if you add reward centering to it is this: you estimate the average reward and you subtract it when you're making the updates. Okay, that is the only change that you make. And so that's the reward centering idea, that do this. And there are different techniques to estimate the average reward, which we'll talk about in a bit. But let's look at, okay, what happens if you do this, right? So one thing is, if you have done some RL, is that you will very quickly know that if you there is a lot of instability that occurs when you use discount factors close to 1, right? And so I'm going to quickly show you some learning curves again. A time step on the x-axis, some notion of reward over time over some moving window on the y-axis. Again, this is what the access control problem. And now I'm showing you the best learning curves after you swept the step sizes for Q learning on this problem. So this one is corresponding to 0.5, 0.8, 0.9, 0.99, 9991, right? So performance improved and then it deteriorated after gamma equal to 0.9. And like, this should come as no surprise to you, right? Like, you've seen this in your experiments. But then if you do this Q learning now with reward centering, look what happens: 0.5, 0.8, 0.9, 99, 991. Monotonic improvement. Okay, no, forget improvement. Like, more importantly, no degradation, right? Which is what is typically happens. But this is tabular. Does it really work with on Atari? Yeah. Okay, so let's start slowly. Let's go with like linear function approximation. Again, 0.5, 0.8, 0.9, 0.99 is also okay, but then you suffer with 99 and 1. If you use Q learning with reward centering, you keep improving, right? Or at least, again, you don't degrade. Okay, this was linear function approximation. What about my neural networks, right? Okay, so now this is a neural network, DQN, 0.5, 0.8, 0.9 is good, but then beyond that, it just doesn't learn anything, right? It's not okay. And then again, if you do this, now there's a bit more variance. I should do more runs of these experiments, but at least you get the rough idea, right? That again, you don't see any degradation as the discount factor, and maybe for 0.5, basically it's maybe just too small to solve this problem, right? Which is fine. Okay, and again, if you look at the parameter studies, all of this is quite robust. If you just do it with Q learning, step sizes on the x-axis, you see some improvement till 0.9 and then things start falling. But if you do it with reward centering, throughout the range of parameters that you could choose, things are pretty good relatively, right? And notice that I've been adding this extra value here, which is this parameter for reward centering, right? Eta. Sounds familiar? And even if I change this value of eta, it's quite robust to the values of eta, right? We started with 1 by 256 all the way to 1. Okay, good. Okay, now what exactly is happening, right? That's the, yeah, what's happening? So again, there's a stream of rewards, and this is the discounted value function, right? The standard one, which we are familiar with, expected sum of discounted rewards starting from state S when you follow policy pi. Now, you can summarize it in the small compact equation. Now, way back in 1962, Blackwell showed this following property, right? That you can decompose the discounted value function into 3 components. Okay, this is a component which are some error terms, and they go to 0 as gamma tends to 1. So let's keep them aside for a moment. This v pi tilde is the differential value function that we've been talking about in the first 2 parts of the talk, right? Which is the value function corresponding to the average reward formulation. Alpha is the average reward scaled with 1 or 1 minus gamma. So if you look at this term carefully, this does not depend on the state, right? If my gamma is, let's say, 0.99, there is a 0.01 in the denominator, which means you're multiplying 100 to the average reward, right? If your average reward is, let's say, 10 for that problem, you have 1000 plus something as your values. These 1000 are not helping determine the quality of the policy in any way, right? It's just an offset. So imagine if you had to choose actions corresponding to this, right? Like the same expressions hold for action values as well. So if you want to take an argmax, this thing does not matter at all. So there is no need to estimate it, right? And that is the thing that is growing super big as your discount factor approaches 1. So let's just forget about it. If you just want to focus on these things, this value function will do it, right? Which is a hybrid of both. It has a gamma, it has a tilde, because you're discounting your rewards, but you're also subtracting the average reward. And then what it does is essentially estimate this minus this, because there's the r pi sum over infinity of this geometric series, which is essentially this. That's a question. Yeah. The good question. That's the next slide. Okay. So yeah. No, so they don't have to be 0 and 1. Does there have to be an upper bound? I mean, it has to have some bound, because like the basically discounting assumes that if you have a discount factor less than 1, for the geometric series to converge, your reward should be bounded by something, but that something need not be 1. Sorry? Yeah, so that would be the bound to the value function. Yes. But we never have to reach it, right? Like just because it is a bound. Okay. And yeah, so you subtract this, and we call this the center discounted value function, right? As opposed to the standard discounted value function. And yeah, some quick intuition about what this large number is. So I've just colored those terms differently, and then we are going to look at this very simple problem. It has 3 states. Just one transition leads to a reward, 3. So if you keep doing this, what reward do you see on average per step? Come on. 1. Okay. So the average reward for this Markov chain is 1. And now let's look at what these different values are, right? So the differential values, it does not depend on gamma. It's 1 for this state because you're going to get a reward, -1 because you got a reward and now you have to go a while, and 0. Now for gamma 0.8, your average reward, which is 1 by 1 over minus gamma, is 5, right? So your standard discounted values are like 6, 4, 5. And if you look at the center discounted values, the difference between the two is basically 5, right? This quantity. These are all close to 1 or 0, and these are all around 5, and they are basically all offset by 5. For gamma 0.9, this offset is now 10, and which is what you see here, right? Around 11, 9, 10. And if you look at the difference between the 10, they're all also 10. For gamma 0.99, this offset is now 100, right? So your discounted values are now close to 100, but the differences between them are still very small. 1, -1, 0, right? And so this is the usual thing, right? So imagine you were trying to assess the quality of the states. The quality is always the same, at least in for these 3 discount factors that we just saw. But then there was this large offset which was getting added. And if you're using a function approximator, maybe when you're trying to estimate 100, you have an error of 2. And that basically screws up any differences between the states, right? So why not just focus on these values, which are just the essential differences between the states, right? So that's what happens when you're doing reward centering. You're estimating the average reward separately. You're not letting it get added with this large factor of 1 over 1 minus gamma to your values. Okay. And
doesn't the bias term take care of this?
One would hope, but yeah, that bias term also has to become that large, right? Something over 1 minus gamma, and it doesn't really turn out to be that way. But if you know what, like the average reward is basically the bias term, right? And we have some intuitions about it, so we can directly set a update rule for it and learn sort of the bias in a separate way, right? Without this 1 over minus gamma scaling factor. And then now back to Tian's question, how are we estimating this, right? Well, throughout over this talk, now you should have become experts in this, right? That in the on policy case, how do you do it? You would just take an average of the rewards that you see, right? On policy, and there's just the usual update rule for it, right? What do you do in the off policy case? The TD error, right? And yeah, that's all. That's all there is to it. But now the TD error looks slightly different, right? It has both the average reward and the discount factor. And then we have results in the paper showing, how good the approximations are under what technical conditions, blah, blah, blah. And yeah, you can take a look at that. And okay, I guess I don't have time to. Yeah, basically, there are two things which are influencing how big this term is: the scaling factor and the average reward. The average reward itself could be a large value, right? And let's say if you are in some part of the world where the rewards are like 0, 1, you go to this, you're a continuing learning agent, you go to the other part of the world, now the rewards are like 10, 11, right? Offset by 10. Suddenly this thing increases. And if you just use Q learning, it is very sensitive to that, right? Now I'm adding these things to all the rewards. And as you can see, performance is very different if you add something. But if you're doing centering, then basically it doesn't make a difference because it quickly learns the average reward and subtracts it out, right? And again, it is robust to the different values of eta parameters. Very nice. Okay, takeaways. Reward centering can improve the performance of discounted methods for all discount factors, and especially as gamma goes to 1. It also makes methods robust to shifts in the problems rewards, right? As you saw, different parts of the world having different these things. And both ways of centering are quite effective, right? If you use just the average of the rewards or the TD errors. But in the off-policy setting, the TD error is more appropriate. And what I'm saying is that now you can use this, like I showed you results with Q learning, but basically just do this for any algorithm that you're using, right? And we have results with like SARSA, even PPO and things like that. And yeah, it's a very small change and gives you lots of benefits. So why not do it? Again, so back to this overall picture, simple and practical algorithms from first principles, right? Super simple. Practical in the sense, again, robust to the parameters that you can set. Everything is based on first principles, which I walk you through. And yeah, you can look at the analysis, more experiments, and blah, blah, blah in this paper, which is currently under review. And it's not a free lunch, right? So there are some caveats, which is now that you're subtracting this average reward as well, that makes your targets even more non-stationary, right? They were already non-stationary because your policy is changing, but now you're also doing something to the rewards. But step-size adaptation can help, where errors are larger, you learn quickly, but when things have sort of calmed down, you can make the step size small so that it's relatively quick, blah, blah. Okay, let me not go into these other things, and I'll just tell you overall, what have we done? So the contributions are, among other things, one-step tabular average reward learning algorithms for on and off policy prediction and control. Well, lots of adjectives. Multi-step average reward learning algorithms for on and off policy prediction using eligibility traces. Then a reward centering idea to improve discounted reward algorithms for continuing problems. All of this to serve this original goal of simple and practical learning algorithms from first principles for long-lived agents. But there's many things to do. Okay, like a lot of people, or at least I had this question from the beginning of my PhD. Continuing problems, what should we use? Average reward discounting. Just tell me one thing, right? Why? So we don't. So I didn't completely answer that question in my PhD, but now I think we have all the tools to do it, right? And to some extent, if you looked at the results closely, the improvement in the reward centering case was all the way up to gamma equal to 1, right? And if you set gamma equal to 1, it is exactly the average reward algorithm, subtracting the average reward, setting your gamma to 1. And so, that wasn't the explicit goal of my analysis, but that is some trends that you're starting to see, right? That if you just use differential Q learning, things could have been pretty good on those problems. The suite of continuing problems, there is a version of it which was released, but there's a lot more in my code base, and I have to make it better and sort of add it to the core base of DeepMind C-suite. You know, all of the things that I worked on were value-based methods. I haven't touched policy-based methods, but there's a lot of people who have developed, you know, average reward TRPO, average reward PPO. There's work going in there, and you know, we can also look into that more carefully. All of the things that I did was model-free methods, right? And you can combine this with planning-based ideas. And exploration is a completely, it's a different beast in the continuing problems, because now you don't have the crutch of resets, which will automatically take you to some maybe nice parts of the state space if you are stuck, right? Like you have to really solve these hard exploration problems now. That needs to be done. Okay, that brings me to the close, and there are many people that I have to thank for these wonderful 5.5 years that I've had here. And so I'll start with my lab group. This is a nice picture with all of us, and we look very happy. And I think, I mean, yeah, it is. It's not, you know, one moment out of it. Yeah, this is, I think, how I basically look for most of my PhD. Right, like it was a good time with lots of good friends, colleagues, and yeah, you know, lots of fun. This was right after my candidacy, and yeah, lots of many good moments throughout this PhD. Some of my closest friends helped me get through the pandemic, and you know, this was a very good time. More friends, more adventures. We are close to the Rockies. I think only when we leave Edmonton we appreciate how good we had it here, and so I'm glad I could experience that with a lot of people here. And you know, you go up the mountains, you can also go down them into tunnels and caves, and that was also fun. But Edmonton itself is super beautiful, and you know, we had a bunch of picnics. We explored the river valley recently through mountain biking. You know, I look very happy in that picture, but what you don't see is from here everything is super bruised because I face planted uh, while doing something. But you know, negative rewards are important for learning, so as you all know. And you know, lots of snowboarding, which we can do here. Lots of hockey too, which I really love that sport. And yeah, I'm very glad that I got the opportunity to play it with uh, a lot of people here, and as well as my teams from outside. And then I would also like to acknowledge my partner who got me through most of this hard part of the PhD, right? And uh, yeah, I can't put into words how helpful that was. And thank you. And of course, it all starts with my family who led me down this path of curiosity and not being afraid to ask questions, and yeah, just enjoying life, right? And if I look like a baby in that picture, that's because I had to go back to 2016 to find a picture of all four of us together, which is so sad, right? And so yeah, I'm going home next week. I will fix that. And yeah, that is about it. Thank you so much for your time. Okay. Was that a question, comment?
Burning questions, or we lose all the time.
Okay, I'm hearing things.
Can I ask you a quick question?
Yeah, go ahead.
Last algorithm. Did you compare it with there are a lot of methods, pop art, or
Oh yeah,
there are a lot of recent methods as well. I forget their name.
yeah. So those so many of those methods, like including pop art and something by Tom Shaw, which I forget the name, they are cool ways to make sure that the parameters that you're learning are in nice ranges, right? As opposed to the quantities themselves. And so, you know, they estimate a lot of clever things using the data stream, like the variance of the TD error, scale down things with that. And so you can combine this with that, right? So and that is one of the things I didn't talk about, that we are talking about any shifts in rewards, right? If you add something to the reward, you can be more robust to it. But if you scale rewards, that is what those techniques help a lot with. And you can combine these two. And I think that will be, when combined with step size adaptation, would be like the way to do credit assignment in RL. Okay, I think we have to leave for the defense. And so, but yeah, if you have any questions, come talk to me after. And I'll be happy to talk to you about it. Recording.